Good morning to everyone. My name is Harshvardhan from Triple E Department. Today topic is about eigenvalues and eigenvectors. Introduction to eigenvalues and eigenvectors. Eigenvalues and eigenvectors are fundamental concepts in linear algebra. They are used to analyze linear transformation and matrix behaviors. Understanding this concept is essential for advanced applications in science and engineering. Basic definitions. An eigenvector of a matrix is a non-zero vector that only changes by a scalar factor when the matrix is applied. An eigenvector corresponds to the scalar vector. Together, they provide insights into the matrix properties. Mathematical notation. If not less of is a square matrix, then an eigenvector not less of V satisfies AV is equals to lambda. Here, lambda is the eigenvalue associated with eigenvector. The equation indicates that applying modulus of A to modulus of V scales modulus of V by lambda. Geometric interpretation. Eigenvalues, eigenvectors can be viewed as directions that remain unchanged under the transformation. Eigenvalues measure how much the transformation stretches or compresses these directions. This geometric perspective helps in visualizing their significance. Finding eigenvalues. Eigenvalues are found by solving the characteristic equation delta of A minus lambda is equal to 0. This equation results from setting the matrix A no less of A minus lambda to be singular. The roots lambda of this polynomial are the eigenvalues. Finding eigenvectors. Once eigenvalues are known, eigenvectors are found by solving no less of A minus lambda V is equal to 0. This involves solving a system of linear equation for each eigenvalue. The solutions from the eigenvectors associated with each eigenvalue. The properties of eigenvalues and eigenvectors. Eigenvalues can be real or complex numbers depending on the matrix. Eigenvectors corresponding to distinct eigenvalues are linearly independent. The set of all eigenvectors can be used to diagonalize the matrix if the matrix is diagonalized. Diagonalization of matrix. A matrix is diagonable if it can be expressed as modulus of A is equals to P into D into P minus 1. In this form, delta of D is a diagonal matrix containing eigenvalues and contains eigenvectors. Diagonalization simplifies powers of matrix and other computations. Applications in differential equation. Eigenvalues and eigenvectors are used to solve system of linear differential equations. They help determine system stability and long-term behavior. This application is crucial in engineering, physics and economics. Principal component analysis (PCA). Eigenvalues and eigenvectors are central to PCA used in data reduction. They identify direction of maximum variance in data sets. PCA helps simplify complex data while preserving important information. Stability analysis in systems. Eigenvalues determine the stability of equilibrium points in dynamical systems. Negative real parts of eigenvalues indicate stability. Positive real parts suggest instability guiding system design. Quantum mechanics. Eigenvalues correspond to measurable quantities like energy levels. Eigenvectors represent the states in which these quantities are well being. This framework is fundamental to understanding quantum systems. Eigenvalues in graph theory. Eigenvalues of adjacency matrix reveal properties of graphs. They help identify graph connectivity and community structure. Special graph theory uses these concepts for network analysis. Computational methods. Numerical algorithms like the QR algorithm are employed to find eigenvalues. These methods are essential for large matrix where analytical solutions are impractical. Software packages like MATLAB and NumPy facilitate eigenvalue computations. Challenges in eigenvalue computation. Eigenvalues can be complex to compute for defective matrix. Multiple eigenvalues may require special handling. Numerical stability is crucial in ensuring accurate results. Summary of key concepts. Eigenvalues and eigenvectors reveal intrinsic characteristics of matrix. They enable diagonalization and simplify matrix operations. Their applications span numerous scientific and engineering disciplines. Practical example 1. Consider matrix modulus of A is equals to modulus of B. 4 and 1 by 2, 3. Solving the characteristic equation yields eigenvalues lambda is equals to 5 and lambda is equals to 2. Corresponding eigenvectors can be found by solving theta of A minus lambda V equals to 0. Practical example 2. For the matrix data of A in the previous slide, diagonalization involves constructing matrix data of P and data of D. Data of D contains the eigenvalues and data of P contains the eigenvectors as columns. This process simplifies computing powers of data of A. Thank you.